This is the last topic in our module on chemical reactivity. The topic for this lesson is reactions involving oxidation and reduction, and we'll be spending some time to look at some of the applications of oxidation reduction reactions, particularly as it relates to electrochemical reactions. And readings for this chapter can be found in, or this module can be found in chapter 17 of the text. Now, there are lots of reactions involving oxidation and reduction that we encounter on a day-to-day basis. Now, some of these include various, in fact, all combustion processes, most metabolic reactions in living organisms, processes which involve the extraction of metals from their ores, the manufacture of countless chemicals, and reactions occurring in the natural environment. For example, corrosion of metals is just one. Now, so what is it that is the commonality in all of these oxidation reduction reactions? Well, at the end of this lecture, we're going to spend some time. You should be able to. During this lecture, we're going to spend some time looking at that, and at the end of this lecture, you'll be able to define effectively oxidation and reduction reactions. Identify some of the fundamental of these types of reactions. For example, identifying oxidizing and reducing agents. Being able to assign oxidation numbers, which is an important prerequisite to being able to identify oxidation reduction reactions. We'll then be spending some time to apply oxidation reduction processes, particularly as it relates to electrochemical cells, and look at some of the fundamentals of these kinds of this kind of application of oxidation reduction reactions. Now we're going to start out by looking at this reaction. What essentially is it that is occurring in a redox reaction? Here we have a beaker of a solution of silver nitrate, and we can see that the solution of silver nitrate is colorless, and we have a coiled wire of copper submerged. After some time, we see that the solution turns blue, and the coiled wire essentially is coated with a thick layer of a solid, which in fact is silver. Now, what is it essentially happening? What we're seeing is that we start out with silver nitrate, so we have Ag plus and NO3 minus ions in solution, and we also have solid copper, but then we end up with a solution of copper nitrate and solid silver. If you look at the reaction very carefully, or think about it very carefully, what you are seeing is that you are seeing some kind of exchange mechanism occurring, where the ions that are in solution, in fact, are exchanged. You started out with silver ions, and now you end up with copper ions in solution, and then you started out with copper solid, and you end up with silver solid. So what essentially is happening in these reactions? Well, essentially what is happening is that there is electron transfer. There is electron transfer from one species to another, and in fact the species which loses the electrons or gives up the electrons is described as being oxidized, and passes the electrons on to another species, which essentially becomes reduced or gains the electrons. And so essentially we have electron transfer occurring, which is as a result of, firstly, oxidation, which allows for the loss of the electrons, and reduction, which involves the gain of the electrons. And so in our reaction, we have the copper solid, which is a copper wire, giving up its 2 electrons to give us copper 2 plus, and so the solution that results is a blue copper sulfate solution, and the electrons that are lost effectively become gained by the silver to form silver ion. Let's go back and look at what happens in oxidation. We have the loss of electrons, and so we have the increase in oxidation number of the copper, and then in reduction we have the gain of the electrons, which results in a reduction in the oxidation number of the silver. Copper the oxidation number is 0, and in copper 2 plus we have an increase in the oxidation number to 2 plus, and in silver we have Ag plus, and we have the acceptance of an electron by that Ag plus, to give us a reduction in the oxidation number of 0 in our silver. So in our oxidation reduction reaction, then we have, as I said before, we have oxidation reduction of, in this case, the oxidation of copper to copper 2 plus, and the reduction of silver plus to silver 0, or silver solid. Now, the fact of the matter is that oxidation and reduction cannot occur in isolation. If reduction is to take place, then oxidation is to take place, and thereby, if reduction is to take place, it means that there is an agent, there is a species that is going to cause reduction to take place, and on the other hand, in order for oxidation to take place, there is a species that will cause oxidation to take place. And we call these agents or species oxidizing agent, where the oxidizing agent is the species that causes oxidization and itself is reduced in the process. And the reducing agent is the agent causing reduction and itself is oxidized in the process. We can call the oxidizing agent an electron acceptor and the reducing agent an electron donor. And so we can typify a redox reaction using this equation. Here we have A2 minus plus B to give us A plus B2 minus, where A2 minus is our reduced species, and it gains electrons to become oxidized to form our oxidized species. And then we have B, which is our oxidized species, which it loses electrons to become reduced to form our reduced species. This depiction shows us simply that we have reduced compound A with its 2 electrons, losing those electrons to become oxidized to form compound A. The reduced compound is the reducing agent, and then on the other hand we have the oxidized compound B, which is called the oxidizing agent, gaining those 2 electrons that are lost from the reducing agent to become itself reduced. Now, a fundamental in order for us to be able to identify oxidation reduction reactions, we have to be able to assign oxidation numbers to various atoms or of elements by themselves or in ions or in molecules. And there are certain protocols or processes that are involved in assigning oxidation numbers, which you should know and which we'll not get into. But so these next few slides here essentially give an outline of how it is that one goes about, in fact the rules for assigning oxidation numbers, which I'll ask you to refer to eventually. Because it forms the basis for us, or for you being able to determine the species that are oxidized or reduced in a redox reaction. What I want to direct your attention to, however, is that when you are assigning oxidation numbers, there are certain questions that you need to follow or ask in order to embark on the systematic approach of assigning oxidation numbers. And a couple of them include: one, is a substance elemental? Is a substance ionic? Is it if the substance is ionic, are there any monatomic ionic species present? Which elements are related to specific rules, and which elements do not have specific rules? And all of these questions will allow you to be able to effectively and systematically assign the oxidation numbers of atoms within specific species in these redox reactions. So let us then move on to identifying oxidation reductions. Here we have an example of what we describe as a Thermite reaction. Now, I had a video, but unfortunately it's not available. But this video, which demonstrates or shows a demonstration of the Thermite reaction, is found in the folder on videos for chemical reactions on My Learning. Now, the Thermite reaction essentially is a very spectacular reaction. As seen from this diagram, it looks pretty much like a fireworks type of a process, and it essentially involves the reaction of aluminum solid and iron 2 oxide or iron 3 oxide to give us iron in its molten state and aluminum 3 oxide. Now, how do we assign the oxidation numbers? We apply the rules as outlined in the previous slides, and in this reaction we see that aluminum in its elemental form, solid, has an oxidation number of 0. In this case, we know that in the case of iron 3, in the case of iron 3 oxide, and I'm saying iron 3 because I know that it's iron 3, we know that oxygen has a 2 minus, and therefore 3 times 2 is 6. And therefore, if we have 2 irons, then the oxidation number of our iron is 3 plus. And here we see on the product side, we now have elemental iron, which tells us that we have a reduction in the iron 3 plus to form iron O, and also we have and also we have oxidation of our aluminum from its elemental form to give us aluminum 3 plus. Again, 3 times minus 2 gives us minus 6, and 2 aluminum, therefore our aluminum species is plus 3. So this is essentially how it is that we're able to, by assigning the oxidation numbers in our species, we're able to actually identify oxidation processes and reduction processes. In this case, aluminum is oxidized to plus 3, and iron is reduced to from plus 3 to 0. Here's another example. Here we have a solution of copper sulfate, which again is blue, aqueous copper sulfate, right? And we have a coil of magnesium submerged into it. What essentially happens? On the right here, we see the result of the reaction. What we see here is a clear solution, which indicates that some chemical change has taken place, and we also see that the copper wire is in fact larger in mass. There seems to be deposits on it. What are the deposits, and what is the nature of the solution that we have? This here is giving us a depiction of what is happening at the molecular level. So we have our metal, magnesium metal, and what happens is that our magnesium metal loses electrons to form magnesium 2 plus, right? And then the copper 2 plus ions that are in solution gain those 2 electrons that are given up from the magnesium to become reduced to form copper. And so we see that the copper atoms now start to deposit on the surface of the magnesium, essentially coating the magnesium. So let us look at the reaction and assign the oxidation number. We have magnesium in its elemental form. The oxidation number is 0. We have copper 2 plus, or copper sulfate solution. The copper has a plus 2 oxidation state. And then we have the formation of our copper metal, which essentially coats the magnesium metal, and so that copper is reduced from copper 2 plus to copper 0, and the magnesium becomes oxidized to magnesium 2 plus, and the magnesium 2 plus are now in the solution. And so we have this clear solution, this colorless solution of magnesium sulfate, as opposed to the blue solution of copper sulfate, and as well magnesium copper deposits on the magnesium. Now, so we just looked at 2 reactions involving oxidation reduction. One that is probably not typical to you. You probably didn't necessarily expect that oxidation reduction reactions take place like that in air, in the case of the Thermite reaction. And then we have oxidation reduction in a typical environment in the aqueous solution. Another typical environment for us to find aqueous, or identify oxidation reduction reactions is in aqueous acids. we have just looked at, we've been looking at, in fact, acidity and basicity in aqueous media, and there are many reactions that take place in the presence of bases and acids, and we're going to look at this one very, very briefly and identify essentially how it is that aqueous or acid have an impact on the stoichiometry of an oxidation reduction reaction. So this reaction is a reaction of potassium permanganate and iron sulfate in acidic aqueous media. Now this reaction is a reaction that I think you will be actually carrying out in the laboratory course, where you're going to be essentially determining the iron content of iron tablets using potassium permanganate. Now let us look at the oxidation reduction reaction. Here we have potassium permanganate, which we are just showing the permanganate anion. Here the oxidation number of the manganese is +7 because we have minus ion, an ion of minus 1 charge, and we know that oxygen has a 2- charge, and therefore 2 times minus 2 times 4 is 8, and therefore the overall value of the Mn2+ is +7. And then here we have iron 2+ in aqueous solution, iron sulfate, iron 2+. And so we have the formation of manganese 2+. So we have the reduction of manganese from +7 to +2, and simultaneously we have the oxidation of iron 2+ to iron 3+. If we look at this reaction, we would see that this reaction is, even though it shows that there is oxidation reduction occurring, it's not balanced. It's in fact not balanced, and it's incomplete. So in order for us to complete it, to show exactly what's happening in the reaction, we have to incorporate exactly what it is that the statement says about the reaction. It says that the reaction was between the permanganate and the sulfate in acidic aqueous solution. And so that means that we have to show the presence of the acidic portion of the equation, and we also have to show the aqueous portion of the equation. And we do this as such here, where we have our permanganate, or iron 2, and we incorporate our acid H+, and then in order to balance the oxygens on the left, we incorporate water on the right, and we can balance the atoms essentially. But this equation is not entirely balanced because the charges are not balanced, and in order for us to balance the charges, we would have to change the coefficients by particular orders, and we ultimately are able to cancel or to balance the charges on both the left and the right hand side of the equation. Now this is a reaction involving oxidation reduction in acids. We can also have similar reactions, not necessarily with potassium permanganate and iron sulfate, but other reactions involving oxidation reduction reactions or processes in aqueous base, and the same principle will apply. Now one of the drawbacks with this with balancing these oxidation reduction reactions in aqueous acid and aqueous base and overall is that we more or less did an arbitrary strategy. We actually employed an arbitrary strategy, but there's a more systematic way of doing it where you have specific steps involved, and we're not going to go through that right here. You should probably be aware of it, familiar with it, but what I'll do is to put up an outline of that on my learning for you to have a look at it. Now we're going to turn our attention to look at the oxidation numbers of nonmetals, because nonmetals, particularly nonmetals, can be very tricky. How do we determine the oxidation state of a nonmetal in an anion per se, or in a molecule? Now there are certain rules that can be applied, and there are essentially 2 rules which can be turned into 4 rules, but they're essentially 2 rules. Now here we have some examples of group 5 anions. We have our nitrate anion, and we have our ammonia. Now the first rule says that the maximum oxidation number of the nonmetal is equal to the atom's group number. So we have in group 5A, we have all of our species having nitrogen, and we want to determine what is the maximum what is the oxidation number of use the oxidation number to tell us something about the oxidizing or reduction potential of that species. So when we look at, for example, the nitrate, we see that the maximum group oxidation number is 5, and therefore in the nitrate N is +5. When we look at ammonia, the oxidation number follows a different rule, and that is the minimum. Nitrogen now acquires the minimum oxidation number, and the minimum oxidation number is equal to the group number minus 8. So in this case, the group number is 5, and so 5 minus 8 gives us -3. And so in this case, we're seeing that the oxidation number on our nitrogen is -3 in ammonia, and that on nitrate on nitrogen and nitrate is +5. What do these oxidation numbers tell us about the oxidizing potential or the reduction potential of these ions? Well, usually when we have the maximum oxidation number of the nonmetal ion being equal to the group the atom's group number, the species tends to be a strong oxidizing agent. Let's go back to look at our nitrate. This is the +5 is the maximum oxidation number that is likely. It means that we cannot go to +6. So nitrate cannot be oxidized to any other species where N is +6. And so that tells us that the other direction or the other possibility for nitrate is to become reduced. So, and it being reduced means that it's an oxidizing agent. And the same thing obtains for our ammonia, but it's the reverse. Because ammonia the nitrogen in ammonia is -3. This is the lowest or the minimum oxidation number, and that tells us that nitrogen cannot be -4. It cannot have an oxidation number of -4, and therefore in this case ammonia can only be the oxidation number can only increase, it cannot become less, and therefore the ammonia becomes oxidized. It can only become oxidized, and hence is a strong reducing agent. Let us look at a couple of other examples. Here we have in group 6A, we have our sulfate, and the maximum oxidation number in this case is, for group 6, is equal to the atom's group number, and in this case it's +6. That is to say that a sulfur has an oxidation state of +6. It cannot get any higher than +6, so it can only become reduced, and therefore it is an oxidizing agent, and a strong oxidizing agent, as a matter of fact. In the case of H2S, on the other hand, the minimum oxidation number in this, the sulfur acquires a minimum oxidation number of -2. In fact, 6 minus 8, right? Group number -8. 6 minus 8 is equal to 2, right? 6 minus 8 is equal to 2, -2, sorry. And therefore sulfur cannot have a lower oxidation number in this species. That is to say that it cannot become reduced any further. And so the only other opportunity for the sulfur in H2S is for it to become oxidized. And hence, because it is oxidized, or it can be oxidized, it is a reducing agent. What of metals? If you think of a metal, metals cannot become anions. Metals can only become cations. And so metals essentially are regarded as reducing agents. Now, there's a series called the reactivity series that ranks metals based on their strength as a reducing agent. And this activity series is what dictates to us, or allows us to be able to determine what is the likely outcome when we have a metal in a solution of another metal ion. So if we go back to our reaction where we had our I think I have it over here, right, where we have our copper sulfate solution, right, and we have our magnesium coil in it. The reason why this reaction occurred to form copper solid and magnesium sulfate is that magnesium is higher in the activity series than copper, and therefore has the ability to displace copper from solution. Alright, so when we go back to our activity series, we see that magnesium is higher in the activity series than copper. In fact, copper is below H2. Copper is in fact a poor reducing agent. That is to say that copper 2+ is likely to be displaced from solution if it is that it reacts with a species that is higher than it in the activity series. So in this case, magnesium being a stronger reducing agent, that is to say that it is likely to become oxidized, says to us that magnesium prefers to be in an oxidized state than over copper being in its oxidized state. And so if magnesium is going to become oxidized in a reaction that involves copper sulfate or copper 2+, it is going to force copper 2+ to become reduced to form copper solid because it's a stronger reducing agent. It has a higher capacity to become oxidized than, say, copper. Alright, so let us explore some of these ideas by looking at this concept question. How it is that if we have various reactions with various metals, metal ions, or other species involving non-metal ions or non-metal atoms, what are some of the likely outcomes of these reactions or oxidation-reduction reactions? So here we have a question. Explain the difference in what happens when a copper-clad penny, which is a US currency, is immersed in A, hydrochloric acid, and B, nitric acid. And here we have some depictions of essentially what happened when those experiments were attempted. So in A, if we look at A, we see that nothing happens. The penny is unperturbed by dissolution or by addition in HCl. But when we add it to nitric acid, we see that a reaction occurs where we form a blue solution, and from our discussions previously, we have copper to form, well, a copper 2+ solution essentially is blue, so it's clearly indicating to us that we in fact have copper being oxidized to copper 2+, but also the evolution of a brown-red, an orange-brown gas. So what is happening, and why are these happening? Why is this happening? Why is there a reaction for the copper in nitric acid and none or no reaction when it is added to hydrochloric acid? Now we go back to essentially what we know about the ability for a metal to become a reducing agent or to become oxidized. If you go back to the table, the activity series, we see that copper again lies much lower in the activity series. It's not much lower, in fact is lower in the activity series, just lower than H2. Right? In our reaction we have in our reaction we have H+ ions and chloride ions as well, right? And it tells us that H+ is likely to become reduced to give us H2O. But because copper lies below the H in the activity series, the copper cannot reduce H+ to give us H2, and itself becoming oxidized to give us copper 2+. And we can also look at it from another angle. We could say that the H+ that is already in solution is not a strong enough oxidizing agent because it's to oxidize the copper metal to copper 2 plus because the H plus is higher. The H is higher in the activity series than the copper, and so we have no reaction. When we look at the one with nitric acid, however, when we go back to our activity series, we see that well, we don't need to go to the activity series now. What we look at here is what are the ions in solution. So we're seeing H plus and we're seeing NO3 minus. We know that H plus is not a strong enough oxidizing agent to cause copper to form copper 2 plus. So it obviously has to be the nitrate. And if you go back to our idea of the oxidation states of the nitrogen or the nonmetal in various species, in particular the oxidation state of N in nitrate, we see that the oxidation state is plus 5. That is the maximum oxidation number that the nitrogen can have, and therefore it is hence a strong oxidizing agent, because it has the capacity to only become reduced from N plus 5 to N plus 4 and plus 3 and plus 2 and so on. So what we see is that because the nitrate is an oxidizing agent and a strong oxidizing agent, because N has the highest possible oxidation number, the copper is being oxidized to copper 2 plus by the nitrate. And so what we have here is copper reacting with nitrate. So we have our copper becoming oxidized and our nitrate becoming reduced to NO2. The NO2 is the gas that we see. And of course, because it is done in aqueous acid, we have to account for our H plus and our oxygen or H2O water. Alright? So since we've now gone through some of the fundamentals, some of the basics of oxidation reduction, we can turn our attention then to looking at some applications of oxidation reduction. And oxidation reduction is a basis for what we describe as electrochemistry, or reactions involving oxidation reduction, or electrochemical reactions. And essentially what electrochemistry is that it's the interconversion of electrical energy to chemical energy. And electrochemistry is an important aspect of the energy industry, where electricity is converted to electrical energy and vice versa, or chemical energy is converted to electricity. And of course we use, in fact, we experience electrochemical processes every day. We use batteries in our cell phones and or various devices, and essentially what's happening in many of those batteries is an electrochemical process, the interconversion of chemical energy to electrical energy. And the basis of this is essentially the movement of electricity or electrical charge. So how do we measure, what are some of the fundamentals that we need to actually extract from an electrochemical reaction? Well, we need to, they involve the movement of electrical charge, so we need to be able to measure this electrical charge, or the movement of the electrical charge. And the movement of electrical charge essentially is current, or electricity, electric current. And what is electric current? The rate at which electric charge passes a particular point. And the unit of measure of electric current is the ampere, which essentially, as you can see from this equation, 1 ampere is equal to 1 coulomb per second, where the coulomb is a charge associated with, it's the measure that is associated with a charge. And if the charge passes a point at a particular time, then we get our ampere, which is coulomb per second. Right? Now, what is the generator of that electric current? How does an electric current become generated? Well, there has to be what we describe a difference in potential between those 2 points, point A and point B. And this potential, which we call the voltage, is the driving force that moves the electrons from one point to another, and in most cases around the circuit for the most part. And this voltage, V, is equivalent to the product of the electrical current and the resistance. So in other words, if the resistance, and we can envisage what resistance is, the ability to block the movement of something, if it is that resistance is very high, then one can have a very high voltage, and if the resistance is very low, then one can have a very low voltage. However, if I'm not sure if this is correct, let me just see if this is correct. By the way, my physics is eluding me. By the way, my physics is eluding me. Right, let's see. Anyways, so the point is that if we have the lowest possible resistance, then the voltage that is associated with that very minimum resistance is called the electromotive force, which is the E cell, and this EMF is what essentially is measured or gives us a measure of the oxidation reduction ability for a particular electrochemical process that takes place in a particular electrochemical cell. Alright, so I've introduced the term electrochemical cells. What are these electrochemical cells? Now, the reactions that we were looking at previously, where we had the magnesium and the magnesium submerged into the copper sulfate, essentially we can, instead of using magnesium, we can use zinc, as shown in this reaction here. Alright, now instead of dipping the magnesium, or in this case the zinc, directly into the copper sulfate, and we have oxidation and reduction taking place in the same flask, what we can do is to separate them. We have oxidation taking place in one flask, and we can have reduction taking place in another flask. And so here we have one flask with zinc nitrate and a zinc metal that is connected to an external wire that passes through an external measure or load, in this case a voltmeter. And then we have another beaker with copper nitrate solution, and submerged into that is a piece of copper metal that is also connected to the external load, in this case the voltmeter. Now, so as I said before, the oxidation reduction processes are separated, but we connect the reactions, or we connect what we describe as the cells, and we'll get into that a little bit more, with what we describe as a salt bridge. This salt bridge here is really a medium through which it has the ability for ions to pass through, so it's an electrolyte, and it just allows for contact between the oxidation side of the reaction and the reduction side of the reaction. And so all of this here now is termed an electrochemical cell, right? We have an oxidation side for oxidation, and not to say that we've determined what side is. One side for oxidation and one side for reduction. We have the capacity to measure the current or the potential passing through the system, and that is through the connection of or connection to electrodes, which are made out of metals. So in this case, the reaction between zinc and copper 2+ to give us zinc 2+ and copper solid is the reaction described as the Daniell cell. And here's a depiction of that. And we're going to look now essentially to see what is exactly happening. Alright, so we have this, instead of having the voltmeter connected, what we have is that we have a light bulb connected to the external circuit. And the fact that there is a light bulb connected and it's lighted, it means that there's the passage of current. Okay? And what we have happening here is that on this side of the electrochemical cell, right, we have where we have the zinc submerged into zinc nitrate, or sulfate or whichever salt, we have oxidation, right? Now the fact that, where is the source of the electrons passing through the circuit? It has to be from one of these cells, and so electrons are being given up by the zinc in this case to give us additional zinc 2+, and the electrons effectively pass through the conductor, the metal, and then enter through the light bulb, and then comes onto passes through the wire onto the copper conductor, and then there is a buildup of electrons on the copper, and they are released into solution to reduce copper 2+ to copper. So over time, what you will see in this reaction is that this zinc electrode becomes diminished because the zinc is oxidizing to form zinc 2+, and this copper is becoming, the mass of it is getting larger, or the size of it is getting larger, because copper 2+ are being reduced to give us and are deposited to the copper metal. Alright, so on this side of the cell, let me just back up before I say that. Now, if you notice that on this side of the cell, where in order to maintain electrical neutrality, you have an excess now of zinc 2+ ions in the solution. In order to maintain electrical neutrality, the salt bridge allows for the balancing of that, where sulfate ions, which would have been in the form of sodium sulfate, passes through the salt bridge and into the solution, and 2- plus 2+ effectively balances the electrical charge on this side of the cell, or in this cell, as we will now call it. And then we see that on this side, Na+ ions migrate down into this side to balance the disappearance, or the reduction in the charge, the plus charge that would have been in the solution. Right? Remember that the copper 2+ is now becoming copper+, and so there's a reduction in the charge. And so to balance that charge, to maintain electrical neutrality, we have to have positive ions, in this case 2 sodium+ ions for every copper 2+. Alright, so on this side of the cell, or in this cell, we call it, what we have happening is oxidation. Zinc going to zinc 2+ to give us an excess of electrons, and then the electrons pass through the circuit to cause reduction, copper 2+ in solution reduced by the electrons to give us copper solid. Alright, now in this cell, the Daniell cell, we have shown that the metals zinc and copper, which are called electrodes, they are essentially a piece of metal that allow for the migration of electric of ions and also the electrons. All right, and these electrodes, zinc and copper, effectively are sacrificed or are participating in the reaction and are called metal ion electrodes. Now, in some electrochemical reactions, you do not have the electrodes participating. In fact, they are inert, and platinum and carbon and so on are examples of those kinds of inert electrodes. So overall, electrochemical cells have this basic setup. We have effectively two half cells or electrodes that are separated electrically from each other, but are connected ionically or electrolytically with each other by a salt bridge. The salt bridge allows for the passage of ions to maintain a balance of charge in the overall electrochemical cell, or in each half cell. And so you have electron flow in a particular direction, and if you were to have connected a voltmeter, if the electron flow is in the expected direction, where you have from what we describe as the anode to the cathode, you have a positive EMF value or a positive E cell value. and we'll look at some of that a little later on. So in the anode, so the compartment that is described as the anode, we have oxidation taking place, and the compartment described as the cathode, we have reduction taking place. So let us go back to our Daniell cell. One of the ways in which we represent electrochemical cells is to use a cell diagram, right? I mean, not all of us are very good artists, and for convenience, chemists, we have devised a way to represent an electrochemical cell very simplistically, and we do so by using a cell diagram. And going back to the Daniell cell, where the reaction is zinc solid plus copper 2 plus to give us zinc 2 plus plus copper solid. This is the archetypal cell diagram, where it essentially represents the electrochemical cell in its strictest and its exact form, its most exact form. And so on the left hand side we have what we call the anode half cell, where we of course know that oxidation takes place. Now in that half cell we have both the electrode, the metal electrode, and the solution. And because the metal electrode is a solid and the solution is a liquid, we have to separate them by what we describe as a boundary phase, or a phase boundary, I should say. Alright, so a solid is one phase and a liquid is another phase, and so to represent that we have two different phases in that cell. We use what we describe as a phase boundary. Now in between the phase boundary we have on the outer side the metal electrode, and on the inner side we have the solution of metal ions. And on the right hand side we have essentially the same thing again, which is a cathode. Of course, we have the phase boundary, right? And on the outer side we have the metal electrode, and on the inner side we have the solution of metal ions. So overall, the cell diagram is essentially depicting the electrochemical cell separating showing the separation of both cells, right? Where the left cell is the anode, where oxidation takes place. The right cell is the cathode, where reduction takes place. There is a phase boundary between the metal and the solution, and because oxidation takes place in the anode, we have the movement or the flow of electrons from the anode to the cathode, and both cells are connected by the salt bridge. So in this case, the Daniell cell, the reaction involving the Daniell cell, shows the anodic side and the cathodic side, where both sides are connected by the salt bridge. The inner part of the cell, or the inner boundary, is the solution of metal, the metal solution I should say, and the outer is the zinc solid, or the zinc electrode, and on the cathodic side we have the inner part of the copper 2 plus solution, and the outer part, the copper solid. So let us look at this idea of electrochemical cells by looking at this concept question. Draw a cell diagram for an electrochemical cell that involves the following overall reaction. Here we have iron reacting with tin 2 plus to give us iron 2 plus and tin. Now what does the strategy involve? Again, we always utilize strategies. Firstly, we need to write out separate half reactions. Right? Remember that half reactions represent either oxidation or reduction. Then from there we determine if we have oxidation and reduction, and then from that we assign oxidation to anode and reduction to cathode, and then apply the phase boundaries and connect the cells using the salt bridge. And so for this solution we have our two half cells, or two half reactions. We have our iron solid to give us our iron 2 plus. Excuse me, something is burning my throat. Here we have iron solid to give us iron 2 plus plus 2e, which is indicating oxidation, and then we have iron 2 plus to give us plus 2e to give us tin solid, which is reduction. Now we need to then determine the sides of the cell diagram that each reaction is to occur on. On the left hand side, we know that it's typical for oxidation, and so we have to write the ions on the inner side and then the metal on the outer, and then the same thing for the right, which is the reduction side. We have the ions on the inner side and the metal on the outer side. Of course, in both cases they're separated by the boundary, and then we connect the cells with the salt bridge, showing the left side separated, or connected rather, by the salt bridge with the right side. And this essentially is the cell diagram for an electrochemical cell, as shown for the reaction shown here, the oxidation reduction reaction shown here. Now, so we've shown essentially reactions of oxidation reduction, and we've indicated we've indicated that these oxidation reduction reactions are measured through the electromotive force, the voltage. Now, how is it that we are able? The fact of the matter is that we can do that for a redox reaction. But remember that a redox reaction involves both oxidation and reduction, and therefore the question is, how is it then are we able to measure the potential, the voltage that is associated with the oxidation and the voltage associated with the reduction? And we do that by essentially finding or referencing the oxidation reaction or oxidation half reaction and the reduction half reaction with respect to that of what we describe as a standard hydrogen half cell, or a standard hydrogen electrode, the SHE. This SHE essentially is a half cell, as shown here, which involves a solution that has H plus ions of concentration 1 mole per dm cube. We have the bubbling of hydrogen gas at 1 bar, and the whole process takes place at 298 Kelvin. And so what happens essentially is that we connect the electrode to well, essentially we say that well, let me not say that. Right, so what is essentially happening in this case? We're having essentially potentially the reduction of H plus ions to give us H2O, and as depicted by this equation, we have H plus to give us 2E to give us H2, sorry. And this the cell potential for this hydrogen half cell is referenced as at a value of 0 volts. That is to say, the potential for reduction of H plus to give us H2 is 0, and we call this effectively the standard reduction potential, where E naught, that's the symbol for standard reduction potential, is equal to 0.0 volts. And so in order for us to determine the potential for other half reactions, we have to connect through an electrochemical cell that cell that we're interested in with this standard hydrogen electrode. And here we have an example of such a measurement from such a cell. So here we have our standard hydrogen electrode connected through the salt bridge to a solution of copper sulfate and copper, and we have our voltmeter measuring the voltage that is associated with the flow of current from one point to another point. Now, how do we determine oxidation and how do we determine reduction? Let us see. In this case, we're going to show the measurement involving reduction. Alright, and here we have let's see. So when we measure the voltage, we see that the voltage is 0.340, which tells us that current is flowing in a positive direction. If current is flowing in a positive direction, it means that current is flowing from, or electrons are moving from the SHE to the cell, the half cell with copper and copper 2+. What is happening here? It means that our H+ ions are effectively our H+ ions are effectively being our H2O gas is effectively being oxidized to H+. If electrons are to flow from this cell into that cell, it means that electrons are being lost, and so the hydrogen is losing the electrons to give us H+. Alright, so for every molecule of H2O, we have the formation of 2 H+ ions. And remember that in the case of the standard hydrogen cell, we are representing reduction, right? And the reduction potential is showing the ability for the H+ to become reduced to give us H2. But in this case, what we're seeing is that this cell is undergoing oxidation, and so we have to reverse the standard hydrogen cell equation and effectively demonstrate oxidation, where we have H2 becoming oxidized to give us H2+, and electrons that are being given up flow through the circuit to now allow for the reduction of copper 2+, right, by those 2 electrons to give us copper solid. And so the EMF that is measured, or the voltage that is measured, essentially is the EMF, or the E cell. But because we know that the SHE has a relative E0, or E cell, of 0, right, of 0 volts, then it means that the reduction potential is effectively representative of the reduction of our copper 2+ to our copper. Alright, so the standard reduction potential, E0, for our copper 2+ copper half cell is equal to plus 0.340 volts. Note that we have oxidation occurring in the standard hydrogen electrode and reduction occurring in the cathode, which is a copper electrode. And so this is showing reduction, the measurement of the reduction potential of a reduction process of copper 2+ to copper. What about oxidation? Here again we have the SHE connected through a salt bridge with a solution of zinc and zinc 2+. But unlike the previous case, we now see that the voltmeter is giving us a measure of minus 0.76 volts. What does that tell us? It tells us that we don't have electrons flowing from our SHE to our zinc. It tells us that we have electrons flowing from our zinc to our SHE. So if electrons are flowing from our zinc to our SHE, it tells us that our normal standard reduction in our SHE cell is occurring. That is to say that we have H+ plus 2E- to give us H2, sorry. Now because electrons are flowing into the SHE, it means that clearly electrons are being lost from our zinc cell, and effectively what is happening is that the zinc metal is becoming oxidized to give us zinc 2+, and the electrons are lost to give us the extra electrons, which now pass through the voltmeter onto the other side and reduce our H+ in our solution to give us H2O. And so this side, the zinc electrode, is the anode and oxidation is occurring, and this side, the SHE, is the cathode in which typical reduction is occurring. And so the EMF that is measured, which is the E cell, is equal to minus 0.763 volts, and hence the standard reduction potential E0 for the zinc 2 plus zinc half cell is equal to minus 0.763 volts. Now, what is it then that these E0 values tell us? Remember that for a particular half cell, we are representing the capacity for reduction or oxidation to take place through what is described as a standard reduction potential. Right? So we're going to be representing all of our half cell reactions as a reduction process. That is to say that we're showing let's go back to here. We're showing a case where we're having an oxidized state gaining electrons to become reduced. Alright? So here we have a table showing reduction half reactions. Right? We represent our half reactions as reduction processes, not as oxidation processes, because we're actually measuring these half reactions in terms of reduction potentials, or the potential to become reduced. And so a listing of various half reactions show a range of reduction potentials. What do these reduction potentials tell us? If we have a high positive reduction potential, it tells us that that half reaction is likely to occur as a reduction. And so, if we look at this one here, where F2 gas is being reduced to F minus, it has a very high positive reduction potential, E0 2.87 plus 2.87. It tells us that this reduction reaction is likely to occur. And therefore, the species in the forward reaction, that is, the species on the left side of the reaction, are regarded as a strong oxidizing agent because they are likely to become reduced. When we go down the series, we see, let's look at lithium. Lithium plus E minus to give us lithium. Again, we're representing a reduction reaction, alright, or a reduction half reaction. We see a negative value, in fact a high negative value, and high negative reduction potential. This tells us that lithium is not likely to be reduced to lithium. In fact, the reverse is likely to happen. That is to say, lithium is likely to become oxidized to lithium plus. And so we say that then that the forward reaction, for the reverse reaction to occur, right? The species on the right is a strong reducing agent, right? Because based on the negative value of the reduction potential, the reduction process is not likely to occur. So just to reiterate, when we see a positive reduction potential, it tells us that the reduction process excuse me, the reduction process is likely to occur. When we see a negative reduction potential, it tells us that the reduction process is not likely to occur, but the reverse process is likely to occur. And so if we have very high positive E0 values, we have very strong oxidizing agents. If we have very high negative values, we have very strong reducing agents. And this here, this series of reduction potentials of half reactions is called the electrochemical series. So, what does this tell us about the capacity for a redox reaction to occur? If, for example, we were to react fluorine with a solution of, if we were to bubble fluorine gas with a solution of, say, zinc 2 plus, would we have a reaction occurring? Or if we were to bubble fluorine or zinc with, or react zinc with magnesium 2, would we have a reaction occurring? And so these reduction potentials essentially help us to be able to determine potentially with respect to each other, if we are likely to have reduction or oxidation occurring. And we're going to explore one of those questions right now. So what reactions would you expect to take place when bromine is added to an aqueous solution containing both NaCl and Na if each is present at a concentration of 1 mole per dm cube? Again, the strategy involves writing out half equations or half reactions. Then we need to consider their E0 values by looking at the electrochemical series, and then from there, from the value of the overall from the combination of the E0 values, decide on the overall reactions. So here we have the half reactions: chlorine being reduced to chloride, bromine being reduced to bromide, iodine being reduced to iodide, and the E0 values are respectively shown. Now, what does this tell us? We see that the E0 for bromine is less than chlorine, right? So the E0 for this half reaction is less than that for chlorine. This tells us that chlorine, if we were to react, it tells us that chlorine is likely to become reduced to chloride more than bromine than to bromide. And so if we are adding bromine in a solution that already has chloride ions, the chloride ions would like to stay in that form, because based on the reduction potential, the reduction potential is fairly high and is higher than that for bromine, and hence the bromine cannot oxidize the chloride to form chlorine. But what we see, however, is that the bromine half reaction has a E0 value that is higher than that for the iodine. It tells us that in comparison to iodine, bromine is more likely to be reduced to bromide. And so what happens is that the iodide is less likely to be in the iodide form, and will hence become oxidized to give us iodine if it is that we add a bromine, which more likely prefers to be in the iodide form compared to bromine. And recognize that if one half reaction shows a higher potential for reduction, then we have to have a reverse process. We have to have if we're going to have a reaction, we have to have oxidation and reduction taking place. So in this case, because bromine has a higher capacity to form bromide compared to iodine, the iodide that are in solution are likely then to become oxidized to give us iodine. But the case does not exist in the case of chlorine, because chlorine already in chloride form is not going to become oxidized to chlorine, because the potential to form the reduced form chloride is higher than for bromine to form bromide, and so on. And so here we have, so having identified what reactions are likely to take place, we say that the bromine is likely to become reduced to form bromide, and the iodide is likely to become oxidized to form iodine, and the overall reaction is this, where the electrons cancel. Alright, so we've looked at really oxidation reduction reaction that would take place in one solution, right, in one medium. Let us now go back to looking at that involving an electrochemical cell. Right, so using now the E0 or the E cell, the EMF of the electrochemical reaction essentially is equal to the E0 for the cathode minus the E0 for the anode. And if we're going to look at that for the Daniell cell, where we know that this is the cell diagram, we can identify the cathodic, right? So we know that the anode occurs on the left and the cathode is on the right, and we can essentially then find the E0 associated with each half reaction and essentially plug that into our equation. So in this case, E cell is equal to E0 for the cathode, which is a copper 2 plus copper half cell, and minus the E0 for the anode, which is a zinc 2 plus zinc half cell. And from the electrochemical series that we just met, we will plug these values in, and it turns out that the E cell for the Daniell cell is equal to 1.10 volts. What does this tell us about the spontaneity or the likelihood of that reaction occurring? Again, because we're measuring well, the overall cell, E cell is a positive value. That tells us that the reaction is spontaneous. But if it's a negative value, that tells us that the reaction is not spontaneous, and in fact the opposite reaction will occur. Okay, so let us summarize what we've learned. We have been introduced to redox reactions, and we've basically underlined that these reactions essentially involve electron transfer, where there is the simultaneous reduction and oxidation of species in the reaction, where reduction essentially involves the gain of electrons and oxidation the loss of electrons. One of the things that we've recognized is that when we look at electrochemical reactions, which are essentially oxidation and reduction reactions, that process is associated with or is facilitated by charge transfer, alright, through the salt bridge or an electrolytic solution. Okay, and that is because both cells which involve oxidation and reduction are entirely separated, but there needs to be a maintenance of electrical neutrality, and that occurs through the electrolyte, which essentially is in the salt bridge. And so overall, again, electrochemical cells involve the oxidation reduction reactions, which allows for electrons to flow through the external circuit, and oxidation occurs at the anode and reduction occurs at the cathode. And half reactions in electrochemical cells are essentially determined with respect to the standard hydrogen electrode as a reference, and these values essentially are able to allow us to calculate, that is say the standard reduction potential, that is the potential for species to be reduced in comparison with respect to a standard hydrogen half cell. The values, the E0 values, essentially are used to calculate the cell potential, which allows us to be able to determine the likelihood for a reaction to occur. And the electrochemical series also allows us to be able to determine the likelihood of a particular reaction through the ranking of the oxidizing power or reduction power of half reactions in terms of their E0 values. Okay, so let us wrap up, and so for the next session I want you to look at these practice questions, and then in exploring the concept to read these 3 boxes, which basically look at very interesting cases of ions, conductivity, electron oxidation reduction processes, and electrochemical processes in various forms. Okay, take care.